I welcome all of you to this class of network analysis and synthesis, and we have started discussion on Laplace transform in the previous lecture. Now we will see that what we mean by transformation and what are the advantages of the transformation. So as an example of transformation, we will take uh, the method of logarithmic. So in case of logarithms, we know that it simplifies multiplications and divisions. So what it does is it simplifies what? It simplifies multiplications and divisions. And if we are interested in extracting roots or raising quantities to the power, we can also, in that case also, we can use logarithms, method of logarithm. But suppose this these two operations, as we are telling that logarithm is going to simplify these two operations. Suppose this is not so convincing. Suppose it is not so convincing. So we can take an example of evaluating uh, one term like this. If we consider this problem, then it becomes clear that logarithm method of logarithm is going to be more convenient provided we are provided with the good table of logarithm. Similar is the case when we want to extract roots. So this method is going to be useful when we want to extract roots, and this one also, like raising quantities to powers. So these are the uh, applications, or these are the operations where advantage of logarithm becomes more clear and logarithm is going to be powerful. Now let us see the overall method of logarithm. So suppose we have two quantities x1 and x2, and we want to evaluate one function, that is y1 is equal to x1 into x2, and another function is y is equal to x1 by x2. So if we want to perform this operation, we can simply perform by normal method of multiplication, and what we get is y1 and y2. Now if I want to use method of logarithm, then what we'll have to do is we'll have to take one's logarithm and then last step will be anti-logarithm, and for these we need tables, logarithmic table and anti-logarithmic tables. These tables are available to us. Now what we do, we get values of log x1 and x2. And as this multiplication operation is to be done in case of logarithmic, this is not transform domain. So in the transform domain, this multiplication is like addition log x1 plus log x2, and this is going to be z1, and if division is to be done, then it is going to be log x minus log x2, and then we get z1 and z2. These are two quantities which are in logarithmic domain. They are not actually y. So using this logarithmic anti-logarithmic tables, we will get corresponding y1 and y2. So here you can see, or anyone will observe, that what is happening here is, rather than going in this straightforward manner, we are doing a roundabout. But why this roundabout? Roundabout is this: first take this transformation, then do this anti-logarithmic inverse transformation. But as we have seen that in these cases, which are not possible by these methods or quite complicated by these methods, here it's going to be still advantageous even if this roundabout is to be done, provided we are having good tables of logarithmic and anti-logarithmic. Similar is the case for Laplace transformation. This logarithm example was an example of transformation. So now, in case of Laplace transformation, we have an integral differential equation The classical method is classical. If we adopt classical solution method, we get whatever is the solution we get here. But if we want to apply Laplace transformation, then on the similar lines as it was in logarithm, we will be taking one transform which is called here Laplace transform, and we have a table here which gives us transform for different components on this side, and then we need to take one inverse Laplace transform which we call inverse Laplace transform, and again here we need a table for this inverse transformation, and when we do this transformation, then we use transformed quantities, transformed values, so we call it transform, and initial conditions are included here, and then we do some. Now here classical method was using some operations where we have a method, we have operations which are not simple operations. But here when we go for transform using Laplace transform, then it allows us to use algebraic manipulation. And through these algebraic manipulations, we get this transform. After these manipulations gives some revised transform. And then using this inverse Laplace transform table, we get the solution. Here again it is a roundabout, but we will see in the coming lectures that it is still advantageous to follow this roundabout, provided we have good tables of transform and inverse transform. Now as an example, we will take a circuit and we'll explain through that how it is advantageous. Although solving circuits through Laplace transform will be explained later on, but here a quick procedure is being given that will explain that how this method is useful. So if we have a circuit which is having DC source V and 1 and 2 are two switch positions, and a switch is here, switch K, which is going to switch, which was earlier at 2 here and is going to this location. So it is switching, suppose at t is equal to 0, and we have one resistance, one inductance and one capacitance, and this capacitance is having some initial charge V naught. This inductor is having some initial current I naught, and suppose, for this to have some initial current and initial voltage, suppose there was some voltage source here. If it is V2, then it is V1. It was like this, and then it is leaving, switch is leaving point number 2, position 2, and is switching to position 1. And under this situation, with the help of Laplace transform, we will get an equivalent transform, equivalent circuit, which we call transformed circuit. Methods of obtaining transformed circuit we will discuss later on. But this part corresponds to inductor. It's a transformed version of inductor. Then we have, and this is a source, voltage source, Li naught is the voltage here. It is in transform domain, this we'll have to remember, and in transform domain this S term comes Ls. Here again a voltage source V naught by S and a transformed impedance, this we call transformed impedance, 1 upon Cs. Ls is a transformed impedance for inductor. And then this voltage source is also transformed. We don't call simply V2. This is V1S. And This is the transformed circuit. This circuit is also not simple, but this R doesn't change in this case. This R remains same, but this L and this C, they get transformed as Ls, C gets transformed as 1 upon Cs. When current through this gives an equivalent voltage source in transform domain Li naught. This voltage here gives P naught by S, a voltage source. And now if you look at the circuit, then we can get this current, and again this current is also I of S, a transformed current. And now we can get expression for this Is, which is simple KVL, you can say, or means sum of voltage drops is equal to supply voltage, or you can say in other words that Is is equal to sum of all sources divided by sum of all the impedances. So sum of all the sources Vn V1s transformed, this is minus 2 plus, this is minus 2 plus, so in the same having same polarity, so it will be added, so it will be Li naught minus 2 plus, this is plus to minus, so polarity is reversed, so it will be V naught by S divided by impedances. So impedance R plus Ls plus 1 upon Cs. This is our current, but this current is, we must remember that it is in transformed domain. We'll have to use inverse Laplace transform to get IT. So this we can represent, even after simplification, we can write down that S times V1S plus Li naught times S, this is not plus, minus V naught S divided by Ls square plus Rs plus 1 upon C. But we have methods to solve, to deal with these. This we will be discussing in the next lectures. So here I will stop, and we will discuss further topics in the next class.